Hello, I am Nikhil, and today I want to take you on a journey into our energy future. Firstly, thank you so much to the organizers of the E3 student contest for giving us the opportunity to participate. My current presentation is a submission for technical presentation challenge, and my topic is energy. I am currently pursuing my second year PhD in Energy and Mineral Engineering department at the Pennsylvania State University. Growing up in a country that relies on coal based power plants for electricity, I witnessed firsthand the environmental impact and the pollution it caused. The thick, smoky, choking the skies and rivers contaminated with pollutants served as constant reminders of the ecological cost of our energy choices. These experiences deeply moved me, sparking a determination to find a clean, more sustainable alternative. It injected in a passion to explore innovative solutions, guiding my path towards advocating for renewable energy sources and environmental conservation. This earlier awareness became a driving force, motivating me to work for a future where energy generation coexists with nature rather than depleting its resources. Energy. Across the globe, energy demand is skyrocketing. Just look at this map. Here, you see that regions with increasing population and energy demand per capita increase are represented in red. Almost most of the regions across the globe have energy demand increase. Global energy demand is projected to surge by more than 50% by 2050. On the other hand, when you observe this figure showing the projection of energy consumption by various energy sources and their share, it is understood that the dependency on renewable energy sources is expected to increase, as you see here. Supplying the world's growing population with clean, affordable energy is a critical challenge for all of us. Now, why are we turning towards renewable energy? It's not just a trend, it's a necessity for all of us. Take a glance of the pie chart here, representing the global emissions by sector. The energy sector contributes 74% of greenhouse gas emissions. And according to Intergovernmental Panel of Climate Change IPCC report, it is expected that our planet is reaching closer to a temperature rise of 1.5 degrees centigrades, a threshold beyond which the consequences could be unimaginable. Climate change is causing a range of increasing impact on the environment. So, what is the solution? Look at the picture here: renewable energy, solar power, wind energy, hydrogen, hydroelectricity. These aren't just alternatives, they are our lifelines. But transitioning isn't just about technology, it's about mindset. It's about understanding that our choices today shape the world of tomorrow. Hydrogen. Hydrogen is a promising energy source due to its high energy content per unit weight. You can observe it in the bar graph showing the difference between batteries and the fuel systems specific energy. Its ability to decarbonize various energy sectors such as industries, transportation, and many other sectors, making it a fuel that has power to transform our future. When we use hydrogen as a fuel in vehicles, the only byproduct we get is water. By harnessing hydrogen production and its potential, we have the opportunity to transition away from the fossil fuels. This transformative ability positions hydrogen not just as a fuel, but as a key player in clean green future where sustainability and innovation synergize to shape a more environmentally conscious world. Imagine this world. I think we'll be witnessing this very soon. Hydrogen fuel cell vehicles offer unmatched advantages over electric vehicles powered by battery. They show superior range and quick refueling time and a lighter weight, making them the perfect clean solution for long distance transportation. Do you know that there are different colors in hydrogen? Haha. Hydrogen has been typically distinguished into three different colors based on the production method employed. Hydrogen produced using fossil fuels that release carbon dioxide into the atmosphere are called gray hydrogen. Hydrogen produced using fossil fuels but with carbon dioxide captured and stored is referred as blue hydrogen. Hydrogen produced through water electrolysis using the electricity generated by renewable sources such as solar, wind, and hydropower are called green hydrogen, making it a truly sustainable and clean energy source. Why green hydrogen? Green hydrogen economy. Green hydrogen economy represents a future where hydrogen produced through clean methods like electrolysis, powered by renewable sources, become the central player in our energy landscape. the production, supply, and the end use. According to CIC research projections, by 2050, it is expected and estimated to meet 18% of the global energy demand and generating an astonishing $2.5 trillion in annual revenue and creating 30 million jobs for all of us. But perhaps the most pivotal aspect lies in its environmental impact. Green hydrogen significantly reduces CO2 emissions by 24%, paving the way to a cleaner planet. Interesting, right? Let's go and generate hydrogen then. So, how do we unlock this immense potential? Through electrocatalytic water splitting. Green hydrogen is produced via electrocatalytic water splitting. We split water into hydrogen and oxygen on a catalyst surface driven by a theoretical voltage of 1.23 volts. Hydrogen is generated through hydrogen evolution reaction, HER. The catalysts play crucial role in facilitating hydrogen evolution reaction. Hydrogen evolution reaction proceeds through a multi-step reaction via two different mechanisms, Volmar-Tafel reaction, Volmar-Hiroshiki reaction, as you see here. In the Volmar-Tafel reaction mechanism, the Volmar reaction takes place first by electron transfer onto the surface and coupling with H3O plus molecules in the acidic medium or H2O molecules in the basic medium. And they lead to adsorbed hydrogen atoms, as you see here. Afterwards, in the presence of a high coverage of this adsorbed hydrogen atoms, two adjacent hydrogen adsorbed atoms diffuse and combine to produce molecular H2. In the Volmar-Hiroshiki reaction mechanism, the first step is still the dissociation process to yield the adsorbed hydrogen atom through Volmar reaction. However, in this case, the coverage of adsorbed hydrogen atoms is low. As a result, this hydrogen adsorbed atom captures a new electron and H3O molecule or H2O molecule to form molecular H2. The catalyst surface plays a vital role in activating water molecule, thereby reducing activation energy required for the reaction. What is the challenge here then? Why haven't we seen hydrogen cars around our streets yet? Hydrogen evolution reaction, HER, requires high over potential, the energy barrier. As we know, catalysts play key role in reducing the energy barrier, and HER active catalyst requires Gibbs free energy closer to zero, as you see in the volcano plot here. There were several noble and non-noble metal-based catalysts which have been explored, and you see they are near to zero Gibbs free energy as you see here. Platinum is currently the state of the art catalyst. Although platinum is effective, it is scarce and expensive, posing a hurdle for scaling up hydrogen production. The challenge lies in the catalyst. As it is expensive, producing hydrogen and getting hydrogen has also become expensive. So we need to find earth abundant catalysts which are efficient and low cost, which will lead us to scalable hydrogen production. Researchers are on the quest for alternative catalysts that are abundant and affordable. This is where my research comes in. I employ density functional theory, DFT, a reliable first principles approach that allows us to peer into the atomic world, predicting properties that are crucial for catalyst design. By focusing on electron density instead of many body interactions, DFT accelerates computations and revolutionizes theoretical prediction. This breakthrough revolutionary idea has been acknowledged by a Nobel Prize in 1998. Density functional theory calculations are performed using simulation package. I currently employ VAST simulation package. We're also exploring quantum espresso. I also use graphical and analysis tools like Methodize, Vesta, Basket, GDIS, and other which are used to model, characterize, and visualize catalyst materials. Earth abundant bio-inspired catalysts. I am currently working on these catalysts. Why? The idea is to basically study and develop novel earth abundant catalysts based on iron nickel sulfide for green hydrogen production. Why is the question. Natural enzymes such as FeNI, FeFe hydrogenase contains FeNI as active sites. As you see here, they contain these active sites. They can catalyze green hydrogen generation with remarkable efficiencies, almost no over potential, and high turnover efficiency. which are comparable to platinum, which is being currently the state of the art catalyst. So this is interesting, right? Hydrogenous offer fascinating blueprints, as I was mentioning, to design novel earth abundant FeNIS sulfide based electrocatalysts. Earth abundant, so here is why we call it. Iron sulfides are earth abundant, inexpensive, and have promising electronic properties for catalyst applications. So these wallerite and gregarite are the catalyst materials I'm currently exploring. Current progress I made. I was involved in a collaborative project where I calculated Gibbs free energy of H adsorption at different sites on RNO, FRNO. They are Fe2NB2O, Ru2NB2O, and FeNBRuO. Basically, I calculated the Gibbs free energy of adsorbed hydrogen at different active sites on these and compared them to determine the stable active sites. The one closer to zero are stable active sites as we studied earlier. This work titled Ruthenium Engineered A2B2O6 Hybrid Columbite Ferrite for Bifunctional pH Universal Water Splitting was published in a renowned Advanced Energy Materials journal. This is a really good news for me, and I am so happy that my work has been published in a renowned journal. I carried out DFT calculations for wallerite materials and generated results as you see here. This is the bulk structure, and this is the density of state of the bulk structure. Basically, this density of state doesn't show any band gap, any gap here, which shows the metallic nature of the wallerite material. And you see here water adsorption on this surface and also dissociation of water molecule here. Impact of my research to the world. This research helps in building strong fundamental molecular level understanding using the DFT, right? For developing bio-inspired earth-abundant iron nickel sulfate electrocatalysts. And this research leverages DFT methodology, density functional theory methodology, to obtain the atomic level insights into the surface, electronic, structural properties of catalyst materials. These insights help in advancing future experimental investigations. These insights are basically the DFT predictions. It is a great benefit to the society as they are addressing the global energy demand with a clean and sustainable green hydrogen adoption. This research falls into the remit cheap and clean energy technologies, ultimately leading all of us to a sustainable future. I always get fascinated by the green hydrogen research as it has a great impact on everyone's life, on, on our lives. These are the list of interesting things which drives me towards my research. The launch of the hubs by United States Department of Energy at different locations in the USA shows how much interest USA has on hydrogen, how it sees the future with hydrogen. And the National Green Hydrogen Mission by India is another inspiration for me. And when I see Toyota, BMW, Honda, and many companies launching hydrogen cars, I always get excited to see how my future and our future will be with these hydrogen cars running all around by just emitting water and creating a sustainable future for all of us. I'm really excited for all of us. And when I got to know in 2020 that Japan, in its Tokyo 2020 Olympics, used hydrogen to lead the torch of the Olympics and called the Hydrogen Olympics, shows how it is seeing hydrogen as a future potential and clean energy source. These are all things, few things which excites me. I always believe that research has to be communicated. And I always feel that I need to understand how the industry is working so that I can drive myself more to get deeper into my research. During the past 1 year of my PhD journey, I had the opportunity to attend MIT Energy Conference, where and I also attended and participated in World Hydrogen North America Conference. This is an industrialist conference where I had the opportunity to interact and learn more about the industry perspective of hydrogen. I presented my research in recent graduate exhibition in March 2023 and was awarded with second place in the video category. Thank you so much for listening to me. I would like to thank my advisor, Dr. Nelson Jade, my research group, Minerals and Materials Theory Group. I also acknowledge the Department of Energy and Mineral Engineering for the assistantship offers, the Institute for Computational and Data Sciences for providing the computational resources, and to my Penn State University for providing me the opportunity to explore my research area. Thank you for listening to me.